Hi, my name is Sanika and I'm presenting my project on multi-label ocular disease classification using deep learning and machine learning models. And I'm the only team member. So let's get started. Ocular disease such as retinopathy and glaucoma, cataract, macular degeneration are major causes of preventable blindness. Screening traditionally requires expert ophthalmologists and specialized equipment which may not be accessible in all regions. And the fundus imaging is widely used non-invasive examination of retinal health, but manual interpretation is slow and subjective. The automated classification system can support clinical decision making and enable large-scale screening. The disease label in real-world data are multi-label since the patient can have several coexisting conditions. Related work. Recent studies show strong success using CNN for retinal disease classification. Use deep attention network for multi-level fundus disease detection, demonstrating improved performance over traditional feature-based method. Then hybrid approaches extract deep features using a pre-trained network and feed them into classical ML. The combined pre-trained CNN feature extraction with classifiers such as SVM and random forest. These techniques work well with smaller dataset. Data description. So we have ocular disease intelligence recognition dataset which contains 3,500 patient records with left and right fundus image. Includes all demographic of age and sex diagnostic keywords are NDG, CHMO. The label includes patient may have multiple disease and the image are taken from multiple devices, variation in quality and contrast. Now the characteristic label distribution highly imbalanced, normal diabetes, other major classes, and the rare condition hypertension, age-related muscular degeneration, pathological myopia. Most patients have only one disease, few have two to three. Data processing steps. The checked metadata, no missing values across 15 fields. Um, Converted image file names full to full path for loading via generator. Converted diagnostic keywords into binary label columns. CNN preprocessing resize 224 into 224 normalized pixel values. Batch generation, a classical model extracted, efficient net features, and standardized scalar PCA transformation. The PCA is applied to standardize efficient net features for exploration and dimensionality. PC1 alone explains 69% of variance. First 10 components explain more than 95% of variance. Then train and test data set, the patient level splitting to prevent data leakage, 80% training and 20% testing, which makes the testing data to be 2,800 samples. Sorry, training data to be 2,800 samples and testing to be 700 samples. Data visualization. The label frequency distribution bar chart summarizes count for each disease. N is normal, D is diabetic retinopathy, dominant data set. The rare classes are HGA have low representation. This imbalance impact model performance. Then next we have number of disease per patient. The histogram showing multi-label distribution. The majority, which is almost 83%, only one disease, while smaller portion has two disease, confers confirms the need for multi-label classification model. Then we have PCA cumulative explained variance. The PCA applied on 120 dimension efficient feature vector. The first component explains 69% of the variance. Top 10 components explain greater than 90%. This indicates high redundancy in embedding space, justifies PCA dimensionality reduction prior to RF training, guided choice of PCA dimension. Then we have F1 score versus threshold score, which is the CNN threshold tuning. The CNN outputs sigmoids probability for each disease level. The threshold section is essential because it determines how probabilities are converted. The key observations are micro F1 and samples F1 peak at 0.25, and the low threshold more labels predict higher recall but higher noise. High threshold fewer label predicted higher precision but poor multi-label convergence. Then we have the overview of method. We have used three model families, CNN, LR, and random forest. Custom CNN with convolution, ReLU, max pooling, dense layering, sigmoid activation for multi-layer outputs, binary cross entropy, and Adam Optimizer class weighting used to address label imbalance, early stopping to prevent overfitting, logistic regression method efficient net VO used to extract 1280 dimensional feature vector from fundus image, feature standardizing with z-score normalization, one versus rest logistic regression train separate classify per labels, provides interpretable linear baseline. Random forest, the baseline is trained with 200 decision trees, use balance subsample, operates 1280 dimension, efficient net features. Innovative approach, efficient B0 is selected for high quality patient level splitting, eliminated accidental leakage. PCA used for both analysis and feature reduction. CNN threshold optimization improves prediction sensitivity. Multiple ML pipelines compared to understand strength and limitations. Model training and evaluation, model trained on 80% data, tested on remaining 20, CNN trained directly on images, LR and RF trained on efficient net embedding, uh, hypermeter tuning, LR tuning C 0.1110 and PCA 50 to 200 components, RF tuning and estimator max step PCA component, CNN tuning focused on threshold selection rather than grid-based architectural tuning. Feature selection, PCA serves primary feature selection method, reduce the dimension from 1280 to 50 to 200 components, helps to avoid overfitting in classical models. Experimental result, the logistic regression base macro F1 is 0.1675, RF the base macro F1 is 0.819, and CNN the strongest model which has the base of 0.4415 and micro of 0.711. Model comparison, CNN demonstrated superior ability to learn from retinal data, LR consists of result benefited from deep feature embedding, and random forest struggles with imbalanced high dimension data even with tuning. The best model highlight is CNN. CNN was most accurate and robust model with a multi-level decision and able to extract spatial retinal features, vessel patterns, and lesion cues directly from pixel data. Conclusion: the three machine learning approaches are developed and compared for multi-level ocular prediction. Deep learning approach CNN outperform the classical models on all major metrics, results, and supports the feasibility of automated fundus screening system. The project completed by in data mining and analytics at UTA. Thanks to the creator of ODIR dataset for enabling ophthalmic AI research.